This is what we'll be learning this chapter in this section. So obviously the scientific method, we start every science class with the scientific method, using the metric system so we have our means of measuring in science, evaluating answers using dimensional analysis, and then performing arithmetic operations. So that's what we're looking forward to here. Physics is the branch of science that involves the study of the physical world. So we have energy, matter, and then how they're related. Mathematics and physics is going to be really important. In physics, equations are important tools, and we will use our note cards again this year. So we're just going to go through an example problem. So if we're looking at electric current, the potential difference, which is the voltage across a circuit, equals the current multiplied by the resistance in the circuit. That is, volts equals I, which stands for amperes, and times R, the ohms. What is the difference of a light or resistance of a light bulb that has a 0.75 amperes current when plugged into a 120 volt outlet? So what we're looking at is how do we solve this problem? So step one, you need to analyze the problem. What are we looking for? Step two, solve for the unknown. So substitute the 120 volts for V and the 0.75 amperes for I. And in doing so, the equation would look like that, and then solving it would be in that. So resistance will be measured in ohms. Step 3, evaluate your answer. I know I emphasized this last year. Does the answer make sense? You know, did you hit it wrong in your calculator? So 1 volt equals 1 ampere ohm, and we haven't learned about the electrical currents yet. You might have in one of your tech classes. So the answer in volts per ampere is in ohms as expected. And of course, we haven't done those. So analyze the problem, rewrite the equation, substitute values. Step 2, solve for the unknown. Then rewrite the equation so the unknown is alone on the left, and then evaluate your answer. SI units. The example problem uses different units of measurement to communicate the variables and the result. It is helpful to use units that everyone understands. And that's where the scientific or the international, the SI units come into play. Scientific institutions have created to define and regulate measures. The worldwide science community will always use the SI or metric system. So SI units, and that's why I had trouble saying it, is because it's French, and so SI doesn't match the International Unit of Standards or standard units. So it uses the 7 base quantities, which are shown in the table below: length, mass, time, temp, amount of substance, electric current, and luminous intensity. And these are the basic units for those, and then the symbol associated with those. And throughout the year, of course, we'll be using these. The base quantities were originally defined in terms of direct measurements. So other units called the derived units are created by combining them. And density was an example of that, mass divided by volume. And obviously, if it's French, then those are regulated by that agency in France. This bureau and the National Institute of Science, NIS, and Technology in Gaithersburg, Maryland, keep the standards of length, time, and mass against which our meter sticks, clocks, and balances are calibrated. And that's important. It's not just willy-nilly. We actually have measurement standards we put them against. And here's a picture of that unit. And they keep it under glass so it can't corrode, can't react with the atmosphere, can't rust, or any of those types of things. And I believe it's a platinum standard. Platinum is the metal they use. So SI units. You probably learned in math class that it's much easier to convert meters to kilometers than feet to miles. The ease of switching units is another feature of the metric system. To convert SI units, you have to multiply or divide by a power of 10. This is all review. I hope this is not boring you to death, but we have to review it. So prefixes are used to change SI units of power 10 as shown in the table below. This is something that maybe we need to put up on the wall so we can refer to it in the future, because we'll need this table. Dimensional analysis. You often will need to use different versions of a formula or use a string of formulas to solve a physics problem. And that will be important. Sometimes it isn't just one that you're going to need to tag team them. So to check that you've set up a problem correctly, write the equation or set of equations you plan to use. I always write down the formula that I'm going to use. You guys have seen me do these problems, and you'll see me do these examples in class tomorrow. Before performing calculations, check that the answer will be in the expected units. For example, if you are finding a speed, you see that your answer should be measured in, will your answer be measured in seconds per meter or meters per second squared? You know you have made an error in setting up the problem. So you want to look at your units. So this method of treating the units as algebraic quantities, which can be canceled out, is called dimensional analysis. So that's where you make sure you have your units in there. Dimensional analysis also is used in choosing conversion factors. A conversion factor is a multiplier equal to 1. We learned this last year. I hope you remember this. For example, 1 kilogram equals 1,000 grams. So you can construct the following conversion factors. That is what we did last year as well. So you choose the appropriate conversion factors so that your units will cancel properly. For example, to convert 1.34 kilograms of iron ore to grams, you do as shown below. You have, and remember, if you remember last year, I had lines instead of the parentheses as just a simplified version. And you see I put kilograms on the bottom because this is understood to be over 1, so that's top, that's bottom, and they cancel each other out. Significant digits again. A meter stick is used to measure a pen, and the measurement is recorded as 14.3 centimeters. This measurement has 3 valid digits. 2 you are sure of, and 1 you estimated. You approximated. It might have been right on the 3, and then you would have said 30. But as far as any other digit after that, you cannot measure to it because a meter stick does not measure to that. So this measurement has 3 valid digits. 2 you are sure of, 1 that's estimated. The valid digits then are called significant digits. All non-zero digits in a measurement are significant, but not all zeros are significant. If you have this example, the first 2 zeros are just a placeholder here. They're just telling you where that decimal goes, and so they are not significant. The last 0, however, is the estimated digit and is significant. When you perform an arithmetic operation, it is important to remember that the result never can be more precise than the least precise measurement. To add or subtract measurements, first perform the operation, then round off the result to correspond with the least precise value involved. To multiply or divide, you're going to perform the calculation, then round to the same number of significant digits as the least precise measurement. Note that significant digits are considered only when calculating with measurements. And again, we will do examples of this to review in class. So I'm giving you the information in this lecture, and then we'll practice it and review and discuss it in class tomorrow. Making observations, doing experiments, and creating models or theories to try to explain your results or predict new answers form the essence of the scientific method. All scientists are going to use this method. It's the way that they are able to communicate with each other as to what they have done. The experiments and results must be reproducible. Other scientists must be able to recreate the experiment and obtain similar data. If not, then the results will not be considered valid and nobody will believe them. Scientists must be able to document and defend what they find. Otherwise, they could be considered to be in that liars group, and you don't want that kind of reputation. So, scientists often work with an idea that can be worded as a hypothesis. This is an educated guess, meaning you must have knowledge about the subject. I don't perform brain surgery, so I cannot tell someone when they need to have brain surgery. So I am not educated, and so therefore I cannot guess why they may need brain surgery or if they need it. So that's what we're talking about. You need to have some sort of knowledge on the subject, and that's where you research. So hypothesis is then tested, and you base, okay, what variables are important and how they're related. You need to have variables, and then you also need to have controls. So hypothesis leads to the experiments, and then models, laws, and theories then come from the experiment. So whatever data you collect, you could build a model, you could create a law depending on how much factual or information you have to support it, and then also theories. I'm going to skip the movie and we'll watch it in class tomorrow to see what they're like and see if it's any good. Models, laws, and theories. An idea, equation, structure, or system can model the phenomenon. Scientific models are based on experimentation. If new data do not fit a model, both new data and the model are re-examined. Nothing is set in stone unless it can be proven. So if a very well-established model is questioned, physicists might first look at the new data. Can anyone reproduce the results, and were other variables at work? If new data are born out of the subsequent experiments, the theories have to change to reflect the new findings. So we're going to go through all these. Whoops, I went one too far. In the 19th century, it was believed that linear markings on Mars showed channels. As telescopes improved, and I keep going on, scientists realized that there were no such markings. In recent times, again, with better instruments, scientists have found features that suggest Mars once had running and standing water on its surface. Each new discovery has raised new questions and areas for exploration. Scientific laws are rules of nature. They sum up related observations to describe a pattern in nature. There's no other explanation today. So we'll talk about refraction and reflection, and that is a law. Light always bends the same way. So I'm going to let you go through these, read these on your own, and then I'm going to click forward and see if you get it right. Okay, that ends that section's lesson, and we tried to keep it under 15 minutes. Sometimes they'll be longer, sometimes they won't. We'll work with this in class tomorrow, and then also the next day we'll do more.